The title of the first module, Group Introduction. Today we are going to see about groups. Let us start from the introduction of a groups. The modern treatment of abstract algebra begins with the simple abstract definition of a group. This simple definition quickly leads to difficult questions involving the structure of such objects. The term group was coined by Galois about 170 years ago to describe sets of 1-1 functions on finite sets that could be grouped together to form a closed set. With that further ado, let us dive into the course. To define a group, we require a non-empty set together with the binary operation. Next, we are going to define the formal definition of group. As in the case with the most fundamental concepts in mathematics, the modern definition of group that follows in the result of a long process. The set is a collection of well defined objects, as we know, and the operation is a function that acts on two elements and results with a single element. For example, addition, multiplication, division, these are the operations defined on number system. Now, we need a non-empty set, we take this as G, and we need a operation, the operation we denote it as star. For our convenience, we take it as star. This set together with this operation have to satisfy some property. Let us go through the property first. First one, closure. Closure means A star B is in G for all A B in G, which means that we have to take two elements A and B in a group. The resulting element, after applying the operation, the resulting element must be in G. If the operation satisfies this property, then the operation is called binary. The second property, associate, which is nothing but we can operate the first two element with the third, which is always same with the operating the last two element with the first one, which means A star B star C equal to A star B star C for all A B C in G. If a set together with this operation satisfies both the property closure and associative, then the set is called, the set with the operation is called semi group. Third one, identity. Identity means we have to find an element, we denote it as E. There exists an E in G such that A star E equal to E star A equal to A for all A in G. So, this element is called identity of the set, and if the group, if a set with the operation satisfies the first three property, namely closure, associative and identity, then the set is called monoid. And the fourth property, inverse. For every element A in G, we have to find an element, we denote it as A inverse of G such that A star A inverse, which is equal to A inverse star A, which is equal to E, which means for every element we have to find another one element in the set which has to satisfy this property. The E is nothing but the identity we have taken from the property 3. So, if the set together with this operation satisfies the first four property, I recall it again, closure, associate, identity and inverse, then the set together with the operation is called group. Next, there are one more property is there, namely commutative. Commutative is nothing but A star B equal to B star A for all A B in G. So, we can able to operate the element in the both the ways, A star B equal to B star A. If the set and the operation satisfies this condition, then the group with this condition, it is called abelian group. So, abelian group means it has to be satisfied the all the five properties. Once again I repeated, closure, associate, identity, inverse and commutative. Suppose a group which a set together with the operation satisfied the four condition, which is called group, and which is not satisfy the last property, namely commutative, then the group is called non-abelian. In 1890, Jordan introduced the term abelian group to honor Niels Henrik Abel, one of the foremost mathematician of the 19th century. Next, we define the formal definition of non-abelian group. A group is non-abelian if there is some pair of elements A and B in G for which A star B not equal to B star A. For clear understanding, we should look for some examples. Let us see some examples. We consider the set of all integers together with the operation plus. So, we define a group, we need a set with an operation for our convenient and the well known set, the set of all integers with the familiar operation plus. So, that means we have to check this form a group or not, for which we have to check the 4 properties. The first one, closure. Clearly, sum of any 2 integer is again an integer, therefore, a plus b belongs to Z for all a comma b in Z. Therefore, closure property is very clear. Next, we are move on to the associative. So, this is also almost clear that a plus b plus c is always equal to a plus b plus c. So, this is always true for the addition. Therefore, Z comma plus satisfy the associative property as well. Next, we are moving on to the identity. Identity means we have to find an element such that a plus that element which is equal to that element plus a equal to a. Can you able to guess what is the element? Yes, it is 0, a plus 0, 0 plus a is a for all element in the Z. Therefore, 0 is the playing the role of the identity. Therefore, the element 0 is the identity in Z plus. Next, we are moving to the last property called inverse. So, which means we have to find an element a plus some element which is equal to this element plus a equal to e. So, in the previous property we identified that the identity element is nothing but 0. Therefore, we have to find an element such that a plus that element is 0. So, obviously that element is nothing but a plus minus of a. So, now we have to check one more thing, that minus a is also be the element in the set Z. It is clear for whatever may be the integer, the minus of that integer is also be the element of the integers. So, this property is hold. Therefore, Z together with the operation plus satisfies the first 4 property. Therefore, the Z plus is group. Next, we on to the last property, namely commutative property. We have to check this because we have to find whether the group is abelian or not. So, it is also again clear that a plus b equal to b plus a for all a in a comma b in Z. Therefore, commutative property holds for Z comma plus. Therefore, Z comma plus is an abelian group. For the next example, we are taking the same set Z together with the operation minus. So, now again the closure property, we know that the suppression of any 2 integer again an integer. Therefore, a minus b belongs to Z for all a comma b in Z. So, therefore, the closure property is satisfied. Therefore, the operation minus is binary operation. Next, associative. In general, the operation minus does not satisfy the associative property in Z. For example, a minus b minus c not equal to a minus b minus c. For which we are consider an example for this, 2 minus 3 minus 4. You can check this, 2 minus 3 is minus 1, minus 1 of minus 4 is minus 5, whereas 2 minus 3 minus 4. So, now first we have to operate 3 minus 4. Therefore, this is minus 1, 2 minus of minus 1 is 3. Therefore, clearly minus 5 not equal to 3. Therefore, in general this associative property does not hold for the operation minus in the set of all integer. Therefore, Z minus is not a group. Next, we move on to another example with the same set of integers together with the different operation, namely product. So, we consider the set of all non-zero integers Z set different with 0 and the usual multiplication cross. We have to verify that this form a group or not, which means we have to verify the 4 properties. The first one, closure. Clearly, the product of any non-zero integer is again a non-zero integer. Therefore, a cross b is an element of Z star for all a comma b belongs to Z star. Next, associative. Clearly, the product of a cross b cross c which is equal to a cross b cross c for any non-zero integers a comma b comma c belongs to Z star. Therefore, the non-zero integers together with the operation product satisfies the closure and associative. Next, the third property, identity. So, identity means we have to find an element for which a cross that element which is equal to the element cross a must be a. So, we have to find such an element. So, in product 1 reserve that element, therefore, a cross 1 which is equal to 1 cross a equal to 1 for all a in Z star. Therefore, 1 is an identity element. Therefore, identity law is also hold. The fourth one, inverse. So, we have to find an inverse for each element. So, A cross some element which is equal to that element cross A which is equal to E, we have seen that E is nothing but 1. Therefore, we have to find an element A cross some element which is equal to 1. So, in set of all integers A cross 1 by A equal to 1. Therefore, we have only A cross 1 by A equal to 1. In integers, take any integer, for example 5, but 1 by 5 it is not an integer. Therefore, in general 1 by A is not an element of Z star except for A equal to 1. Therefore, the inverse property does not hold even though there are some inverse exist, but the inverse is not in the set. Therefore, inverse property does not hold, but it satisfies the first 3 property. Therefore, Z star comma the usual product is a monoid. Next, we can check for the commutative. The commutative law is always hold for product. So, A cross B equal to B cross A for all A comma B in Z star. Therefore, commutative law always hold for Z star comma product. Next, there are one more operation remaining in set of all integers, that is division. Therefore, we again check the set of all non-zero integers together with the operation division is form a group or not. Let us check the first property, closure. We know that A divided by B is not, in general it is not an element of Z star. For example, take 2 and 3, 2 and 3 both of them element of the integers, but 2 by 3 is not an element of the integers. Therefore, even the closure property does not satisfy. Therefore, the division operation is not even a binary. Therefore, the Z star comma integer set of all non-zero integers together with the operation division not form a group. So, now we are familiar with set of all integers. So, set of all integers together with the operation addition form a group, even it is an abelian group, but set of all integer together with the operation minus not form a group. Set of all non-zero integers together with the operation product and division not form a group. Now, we are consider another important set of all real numbers. So, now consider set of all non-zero real numbers together with the usual product cross. R star denotes set of all real numbers with set minus 0. This means set of all non-zero real numbers. We are just avoiding 0 from the real numbers. We have to check this R star comma cross form a group or not. Closure, clearly A cross B is an element of the set of all non-zero real numbers for all A comma B belongs to R star, because product of any two real numbers is again a real number. Therefore, this closure is always true. Next, associative. Associative is obviously clear. A cross B cross C equal to A cross B cross C for all A comma B comma C belongs to R star. Next, we move on to identity. That means we have to find an element A cross some element which is equal to that some element cross A equal to A for all A belongs to R star. So, here again in product the element 1 doing deserve this 1, therefore, A cross 1 cross A equal to A for all A belongs to R star. This 1 is also an element of the non-zero real numbers, therefore, 1 satisfies the identity property. Next, the last property for the group, inverse. So, we have to find an element for every element A cross that element which is equal to that element cross A is an identity. As we seen in the third property, the identity is 1, therefore, we have to find an element A cross some element equal to 1. So, again in multiplication A cross 1 by A equal to 1, therefore, 1 by A may be the inverse of every element, but we have to find that this 1 by A is an element of the non-zero real numbers. Yes, of course, in case of non-zero real numbers, since we are avoiding 0, 1 by 0 is undefined, therefore, the 0 is eliminated from R star. So, this is the reason we have removed 0 from our set. Therefore, 1 by A belongs to R star for every non-zero real numbers. Therefore, inverse property also again hold for R star comma cross. Therefore, R star comma cross form a group. So, again we have to check one more property for verifying the abelian or not. So, commutative property A cross B equal to B cross A for all A comma B in R star. Therefore, commutative property is always hold. Therefore, this R star comma cross form an abelian group. Now, we are going to use another technique, namely Cayley table, for checking a group property for any finite set. Cayley table is an effective tool to find whether a finite set together with an operation is a group or not. A Cayley table describes the structure of a finite group by arranging all the elements in a square table. It is named after the 19th century British mathematician Arthur Cayley. In the first example, we are considering set of all cubic roots of unity g equal to 1 omega omega square under its multiplication. So, we take the set g equal to 1 omega omega square, which are nothing but the cubic root of unity. Therefore, omega power 3 equal to 1, the operation is the product here. Okay. So, now we are going to check whether this set together with the operation product form a group or not by using the Cayley table. So, as we already said, Cayley table is a squared table by arranging the elements of the set by row and columns. Therefore, 1 omega omega square are the elements of the group. Therefore, we are arranging the rows and columns by row 1 omega omega square and by column 1 omega omega square. We are going to apply the operation product. So, how we do this? First, we are fill the entire elements of the Cayley table by 1 into 1 is 1. Therefore, we have placed 1 here, 1 into omega which is equal to omega. Therefore, omega is placed here, 1 into omega square is omega square. In the next row, omega into 1 omega, omega into omega omega square, omega into omega square equal to 1 because omega cube is 1. The last row, omega square into 1 omega square into omega 1, omega square into omega square which is equal to omega power 4. Since omega power 3 is 1, this is equal to omega. This is how we are enter all the elements of the Cayley table. Now, we move on to the properties. The first properties says closure. Closure means the product of any two elements is again an element of the set. Here you look at all the entries 1 omega omega square, omega 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 square, omega square 1 omega. Therefore, all the entries of the tables are the elements of the group. Therefore, closure property is very clear from the table. Next, the associative property, it can be also clearly verified from these 9 entries. The associative is always true. The next property identity. So, we have to find an element from this set which satisfies the property that A star the element which is equal to the element star A equal to A for all A. So, here you look at this 1 dot 1 is 1, 1 dot omega equal to omega, 1 dot omega square equal to omega square. Therefore, 1 doing the identity properties. Therefore, any element dot 1 is equal to the same element. Therefore, 1 is the identity here. The last property inverse. So, we have to find an inverse for each of these elements. Here note that 1 into 1 is 1. Therefore, the inverse of 1 is self inverse 1. Next, we have to find the inverse for omega. So, that means omega is here. We have to find the entry 1 among these 3. So, the entry 1 is here. Therefore, the inverse of omega is omega square. Therefore, omega into omega square equal to 1. Similarly, the other way omega square into omega is also 1. Therefore, the inverse of omega is omega square. For the last element omega square, come back again here, omega square, the entry 1 is here, the corresponding entry of the column is omega. Therefore, omega square into omega is 1, and the other ways omega into omega square is also 1. Therefore, the inverse of omega square is omega. Therefore, all the 3 elements has an inverse. Therefore, the inverse property is also satisfied. Hence, the cubic root of unity together with the operation product form a group. Again, you can check this is also satisfies the commutative property. Therefore, this form an abelian group. More general, we can consider one more example, the set of all nth root of unity. The elements are 1 omega omega square up to omega power n minus 1. The similar way you can able to draw any Cayley table for a finite set. You can try to find the Cayley table for 1 omega omega square up to omega power n, which is nothing but the nth root of unity, which means omega power n equal to identity. This set together with the operation product is satisfies all the 5 properties, and for this is also form an abelian group. Next we consider one more example, but this time the set is set of all integer modulo 4 together with the operation addition modulo 4. I hope you are somehow familiar with this set. Even then, the set Z4 is nothing but the element 0, 1, 2, 3. So, the element of Zn is nothing but the element 0, 1, 2 up to n minus 1. Now, we come to the operation. We are considering here the addition modulo 4. The addition modulo 4 means we have to add the 2 elements with the addition modulo 4, means a plus addition modulo 4 b is nothing but a plus b if a plus b is less than 4, and otherwise it is r is nothing but the remainder when you divide a plus b by n. So, r, I repeat again, r is nothing. So, this is a finite set. So, we are going to find whether this set together with this operation form a group or not. So, since this is finite, we are again going with the Cayley table. So, the rows are entered by the element 0, 1, 2, 3, and the column is also entered by 0, 1, 2, 3, and the operation addition modulo 4. Let us see how we fill up this. 0 plus 0 is 0, 0 plus 1 is 1, 0 plus addition modulo 2 is 2, 0 plus 3 is 3, because these are the elements less than 4. Therefore, we just replace addition modulo 4 by the addition. Next, 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3. Again we have the elements less than 4. Therefore, in place of addition modulo 4 we just adding the 2 elements. Now, come to the last one. 1 plus 3 is actually 4, which is greater than or equal to 4. That means we have to find the remainder. So, the remainder, now we get 3 plus 1 is 4. When we divide 4 by 4, the remainder is 0. Therefore, 1 plus 3 is 0. Next column, 2 plus 0 is 2, 2 plus 1 is 3, 2 plus 2 again 4. When we divide 4 by 4, the remainder is 0. 2 plus 3 is 5 actually. When we divide 5 by 4, the remainder is 1. The last column 3, 0 plus 3 is 3, 0 plus 1 is 4, therefore 0, 2 plus 3 5, therefore 1, again 3 plus 3 is 6. When we divide 6 by 4, the remainder is 2. This is how we fill up this entire Cayley table. Now, we are verifying the properties. The first property, closure. So, here again all the elements of the Cayley table, all the entries of the Cayley tables are the elements of C4. Therefore, the closure property is true. Again associative is clear from the Cayley table. Now, we move on to the identity. So, that means we have to find an element which satisfies the property that A addition modulo 4 plus the element is A for all A. Now, look at here 0, 0 doing this job for us. That means 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3. Therefore, 0 plus any element is again that element. Therefore, 0 is an identity which is also an element of the Z4. Therefore, it satisfies the third property, identity. The last property, inverse, that means we have to find inverse for each element. Inverse of 0 is nothing but 0. Next, we have to find the inverse for 1. That means we have to find the inverse for 1, which means we have to find the identity from this column, the second column. So, the identity is 0, which is placed in the last row of this Cayley table, which means the inverse of 1 is 3. Therefore, 1 plus 3 is 0. Therefore, the inverse of 1 is 3. Next, we have to find the inverse for this next element 2. That means we have to find 0 here. 0 is in the third row of this Cayley table, which means the inverse of 2 is 2. Therefore, 2 plus 2 is 0. Therefore, the inverse of 2 is 2. Again, for the last element we have to find the inverse for 3, which means we have to find the 0. 0 is placed here. Therefore, the inverse of 3 is 1. 3 plus 1 is 0. Therefore, inverse of 3 is 1. So, we have find the inverse of 0 is 0, inverse of 1 is 3, inverse of 3 is 3. Therefore, inverse property is also satisfied, therefore, this form a group, and we have to check one more property for the abelian group. Here a plus b, a integer modulo 4b is again b integer modulo 4, it can be easily verified. Therefore, Z4 together with the operation integer modulo 4 form an abelian group. So, it can be also generalized to the general set Zn. So, any integer n. So, Zn is nothing but 0, 1, 2 up to n minus 1 with the operation addition modulo n. So, the set Zn together with the property together with the operation integer modulo n form an abelian group. Next, we are going to discuss about the Z4 with the multiplication modulo 4. So, consider the same set G equal to set of all integer modulo 4 0, 1, 2, 3 together with the operation multiplication modulo 4, which means that A multiplication modulo 4 B is nothing but A cross B if A cross B is less than 4, and otherwise it is a remainder when we divide A cross B by n, then the remainder is R. The R is the product of integer modulo 4 of these two elements. Now, again we are consider the Cayley table 0, 1, 2, 3, 0, 1, 2, 3 the elements of Z4 together with the operation multiplication modulo 4. So, 0 cross 0 is 0, 0 cross 1 is 0, 0 cross 2 is 0, 0 cross 3 is 0, and 1 cross 0 is 0, 1 cross 1 is 1, 1 into 2 2, 1 into 3 3, 2 into 0 0, 2 into 1 is 2. So, now up to now all these elements are less than 4, therefore, we have just replaced with the product, and 2 into 4 is 4 actually. Therefore, when we divide 4 by 4 the remainder is 0, and 2 into 3 is 6, when 6 divided by 4 the remainder is 2. Again similarly for the 3, 0 into 3 is 3, 1 into 3 is 3, 2 into 3 is 6, therefore, integer modulo 4 the answer is 2, 3 into 3 is 9, the integer modulo 4, so that means we have to divide 9 by 4, we get the remainder as 1. Therefore, this is the Cayley table. Now, here you look at it 0, the entries of the first row is all of them are 0, and therefore, this is satisfies the even closure property and associative, but it is not satisfies the identity property. Here you can check that 1 is identity because 1 anything is 0, therefore, we cannot get the identity as well as the inverse for 0. So, now the question is even if you remove 0 still we can get the group or not. So, just forget this the first row as 0 row and start from here 1 2 3. Now, 1 into 0 is 0, 1 into 1 is 1, therefore, the inverse may be 1. So, we have to check it out 1 into 1 is 1, 1 into 2 is 2, 1 into 3 is 3, but when you come to 2, 2 into 2 is 0. So, 0 is repeated twice, which means that 2 into 2 is 0, we here there is no 1 here, which means the inverse property does not satisfies for the element 2. So, even if we remove 0 from this set, that means Z4 star, still we cannot get a group with the operation multiplication modulo 4. So, in general both Zn as well as Zn star, which means Zn equal to 0, 1, 2 up to n minus 1, and Zn star means 1, 2 up to n minus 1 with respect to the multiplication modulo n does not form a group. Next example, we consider set of all complex numbers with the operation complex addition. Set of all complex numbers denoted by C, which is nothing but set of all C equal to set of all x plus I y such that x comma y belongs to R real numbers. So, now we consider the set C together with the operation addition complex addition. Therefore, the combination addition is defined by a plus I b plus c plus I d equal to a plus c plus I of b plus d. So, this is again a complex number. Therefore, the first property closure is very clear from the definition of addition. Next, associative. So, consider the 3 complex number, we take it as a plus I b, c plus I d plus e plus I f. Now, we have to add these 3. So, a plus c these are the real component plus I into imaginary component b plus d plus f. So, this is the imaginary component. Now, it can be written as a plus I b here and plus c plus I d and E plus IF. So, here the addition is associate in case of the real number R, therefore, this is happens, therefore, this set of all complex number is associate. Third, we come to the identity property, which means we have to find a complex number such that the complex number plus a plus any a plus ib which is equal to a plus ib and the complex number which is equal to a plus ib. So, it is very clear that 0 plus I 0 is an element of the complex number which satisfies this property 0 plus I 0 plus a plus ib which is equal to a plus ib plus 0 plus I 0 is always a plus ib. Therefore, 0 plus ib is an identity element which is also an element of a complex number. And the fourth property, inverse, that means we have to find an inverse for each element. So, take a plus ib, which means we have to find one more element here which has to be satisfied that the element plus a plus ib which is equal to a plus ib plus an element which is equal to 0 plus I 0, which is an identity element which differs in the property number 3. Now, here again a plus ib we have to get 0 plus I 0, therefore, both real and imaginary part is 0, which means minus a plus I of minus b, which means minus of a plus ib is the inverse of each element, which is also an element of the complex number, because this is nothing but minus a plus I of minus b, minus a and minus b are the element of the real number. Therefore, this is again a complex number. Therefore, for every a plus ib, minus of a plus ib is an inverse, additive inverse. Therefore, complex number with this addition satisfies all the 4 properties, and hence this is a form a group. So, we very well clear about a plus ib and c plus id, which is equal to a plus ib plus ib plus d, which is equal to a plus id and c plus id. Therefore, this is commutative. Therefore, C set of all complex number together with the complex addition form a abelian group. Next, we consider the one more operation in complex number called complex product. So, consider the set non-empty set C set of all complex number together with the operation complex multiplication. So, here the complex multiplication is take 2 elements from the complex number a plus ib and c plus id, where a, b, c, d are the elements of the real numbers. Then the product is nothing but product these two a c and I into a d here, and then I into b c, and the last one plus I square b d. Okay. So, now this is a c minus b d. You see I square is minus 1. So, this is nothing but plus of I square, therefore, I square is minus 1, therefore, this is minus b d, a c minus b d plus I into a d plus b c for all a b c in R. Now, consider the first property closure. Clearly, the product of 2 complex number, again a complex number, because a c minus b d is a real number and a d minus b c is also a real number, therefore, this is a complex number. Therefore, the product of 2 complex number is again a complex. The second one associate, it can be verified easily that a plus ib cross c plus id, which is product with e plus if, which is always equal to the product of c plus id plus e plus if with a plus ib. Therefore, associative law always hold for complex numbers. Next, we have to find an element which is a complex number in which a plus ib cross some identity which is equal to some element class a plus ib which is equal to a plus ib. So, here you can note that this is the product. So, take 1 plus I 0, 1 plus I 0 is an element, take 1 plus I 0 and now product a plus ib with 1 plus I 0, that means here there are only one element 1, which means this is a 0 element, imaginary part of the second one is 0, therefore, a plus ib is again a plus ib. Therefore, 1 plus I 0 is an identity element which is an element of the complex number, therefore, which satisfy the complex property identity property. Fourth one, a plus ib into some element I have to find such a way that again the element plus a plus ib equal to 1 plus I 0. So, we have to find a complex number here which satisfies this property, which means I have to find a plus ib by 1 plus a plus ib. So, 1 by a plus ib may be exit or may not be exit in complex number. So, we have to verify that 1 by a plus ib is a complex number or not. So, in which we have just multiply 1 by a plus ib by the conjugate a minus ib by the a minus ib, therefore, a minus ib by a plus ib into a minus ib. We know this is nothing but a square plus b square, because the first term is a square and minus of I square b square, which is equal to a square plus b square, and the remaining two terms are head cancel, therefore, this is a square plus b square. Now, this can be written as the real part and the imaginary part. So, a by a square plus b square, the real part, plus the imaginary part I into minus of b. So, I into minus of b by a square plus b square. So, this is the complex number, therefore, the 1 by a plus ib is always exist. So, this is the form a group, and finally, we have verified the commutative property a plus ib into c plus id is AC minus BD plus I into AD plus BC as by the definition of the product of complex number, which is equal to, now I have changed this to A and C because A and C are the elements of the real number. So, I can able to change A and C, therefore, AC equal to CA minus BD plus, and again I change AD by DA plus CB. Therefore, this is nothing but C plus ID into A plus IB. Therefore, A plus IB into C plus ID is always equal to C plus ID into A plus IB. Therefore, the complex product is commutative. So, set of all complex number with complex multiplication satisfies the first four properties of group. Therefore, C cross is group. Next, we move on to the last property, namely commutative. A plus IB cross C plus IB, which is equal to AC minus BD plus I into AD plus BC by the definition of the complex product. And now, I like to interchange AC by CA, because this can be done because A and C are the elements of the real number. Therefore, I can change AC by CA. Similarly, I can change BD by DB. Therefore, AC minus BD. On the other hand, also AD I change AD by DA and BC by CB. Therefore, I into DA plus CB. So, this is now again we are like to go from the product to the definition, which means C plus ID into A plus IB. Therefore, the A plus IB into C plus ID, which is always equal to C plus ID into A plus IB. Therefore, complex multiplication is commutative. Hence, the set of all complex number together with the operation complex product is an abelian group. Finally, we consider one more example. Here the set is collection of all 2 by 2 matrix. In particular, we consider 2 by 2 non-singular matrices. So, let G be a set of all 2 by 2 non-singular matrices. Together with the matrix multiplication operation, we have to verify that this G is form a group or not. So, the first property, so we well known that the product of two by 2 non-singular matrices is again a 2 by 2 non-singular matrix. Therefore, A cross B is always an element of G. Again, the associative is always clear in terms of matrix multiplication. Therefore, A cross B cross C is always A cross of B cross of C. So, this is always true in case of matrix multiplication. Therefore, it is also true in case of 2 by 2 non-singular matrices. So, associative property satisfies. Next, the identity property. So, that means we have to find an identity, that means A cross and the identity element, which is equal to the identity element cross A equal to A for all A in G. So, we have to find such a element. So, the such element is nothing but 1 0 0 1. So, here we have checked that, take any general 2 by 2 non-singular matrix, namely A B C D, where A B C D are the elements of the real number, and we product A B C D with the 1 0 0 1 2 by 2 non-singular matrix. This is non-singular also because the determinant of A is nothing but 1 into 1 minus 0. Therefore, determinant of this matrix is 1, therefore, which is not equal to 0. Therefore, this is a non-singular matrix, and therefore, this matrix is always an element of G. Now, we find this matrix satisfies the properties of identity or not. So, product these two, then you get the first row and the first column, which means A into A plus 0, therefore, A, the first row and the second column, which means 0 plus B, therefore, B, and likewise for the third and fourth element. So, which is nothing but A B C D. Again, now this is also equal to 1 0 0 1 into matrix multiplication with A B C D. You can check here also the first row and column, which is nothing but A plus 0, therefore, this is A, and again first row and column B into 0, so therefore, B. So, likewise, this is a product of A cross, we may assume this as I. So, A cross I equal to I cross A, which is equal to A, this I is an element of G, therefore, this I do the identity properties. Next, last we consider the fourth property, that is inverse. So, that means I have to find an element in the set of all 2 by 2 non-singular matrix in such a way that A cross the element which is equal to A the element cross A which is equal to the identity. So, just now we have seen that the identity is nothing but 1 0 0 1, therefore, I have to find some element for each A to satisfy this equation. So, we know that this element we just denote it as A inverse, this is nothing but 1 by determinant of A into edge of A. Now, we have taken only a non-singular matrices in our G, therefore, this determinant of A is always not equal to 0, therefore, this term is always exist and which is also an element of G, because of adjoint of A is again a 2 by 2 matrix and this gives the non-singular property also, therefore, A inverse is always an element of G. To satisfy this equation, we have taken all non-singular matrix, otherwise we may take any 2 by 2 matrices, but it is if you take any 2 by 2 matrices, then this equation does not exist for all A, therefore, we have considered only 2 by 2 non-singular matrices. Therefore, this set of all 2 by 2 non-singular matrix together with the matrix multiplication form a group. Next, we check the last property, which means for checking abelian commutative property. In general, we know that the matrix multiplication, any matrix multiplication is not commutative here that is true also in 2 by 2 matrices also. Therefore, G comma matrix multiplication is a non-abelian group. Up to now, we have seen several examples of semi groups, monoid, group, abelian group and non-abelian groups. Now, as a tabular format, we summarize the axioms of a group in the order for a particular operations. There are some questions in our mind. We have seen about the identity of a group. Is the identity of a group is unique? The first question. The second question is inverse. We have seen that in a group for every element we have an inverse. Is this inverse is unique, or we may have more than one inverse for every element? So, this is our second question. Now, we are going to answer these questions by seeing some of the statements. So, the first statement, uniqueness of identity, which means the identity is unique. We are going to prove that if G is a group, then the identity of a group is unique. Suppose we may assume in the quantity that there are two identities exist for a given group. Let E and E prime are the two identities of a group. Then by the definition of the identity, we have AE equal to A for all A in G. Similarly, by the definition of the identity in case of E prime into A equal to A for all A in G. So, now take the first one is equation 1 and second one as equation 2. Now, by these two equations you have seen that this is true for all A. So, which means in particular this is true for E prime also, these two are two different elements. Therefore, AE equal to A means this is also true for E prime, therefore, I can choose A as E prime, which means I have apply instead of A E prime, which means E prime into E equal to E prime. So, here it is. So, E prime into E equal to E prime. Next, in the equation number 2, this is true for all A, which means this is also true for the E, therefore, I choose instead of A by E. Therefore, E prime into E which is equal to E, therefore, E prime into E equal to E. Now, combine these two equations, see the left hand side E prime into E, here also E prime into E, therefore, the right hand sides are equal, which means E prime equal to E. Therefore, this is not two different identity, both of them are same. Hence, the identity of a group is always unique. Next, cancellation law. We are going to see about the cancellation law. First of all, note that cancellation law is not valid everywhere. For example, consider Z6 set of all integer modulo 6 together with the multiplication modulo 6 operation. This is a set together with the operation integer modulo 6. Here the elements of Z6 are 1, 2, 3, 4 and 5. Therefore, I take 2 and 3. the integer modulo 6 with operation with 2 and 3 is 0, because 2 into 3 is 6, and if we divide 6 by 6 the remainder is 0, therefore 2 into 3 is 0. Again consider 4 and 3, now apply the integer modulo 6 for 4 and 3. So, 4 integer modulo 6 with 3 is actually 12, we have divided 12 by 6, the remainder is again 0. Therefore, these two products are equal, therefore 2 into integer modulo 6 3, which is equal to 4 integer modulo product of integer modulo 6 into 3 are the same. Now, suppose the cancellation law is valid, means we can able to cancel 3 into 3, which means 2 equal to 4, but in Z6 2 never equal to 4. Therefore, this is the contradiction, therefore, cancellation law is not valid everywhere. Now, the question is, then when the cancellation law is valid, we have a tool, that is a group. In case of a set together with an operation form a group, then the cancellation law is valid. So, here we are going to prove this. Suppose we take BA equal to CA, there are two elements of a given group G. Suppose these two elements are equal, then B equal to C, that means we can cancel A and A, which get C. This is called the right cancellation law. Similarly, suppose AB equal to AC are equal, then B equal to C, that means we cancel the A in the left hand side, which means this is the left cancellation law. Therefore, cancellation law is hold in case of a group together with the operation. So, here B dot A means operation of a group. We see this proof, suppose BA equal to CA. So, I am taking this BA equal to CA, let A inverse equal to A prime, because we are in the group, for every element inverses exist. So, A also has an inverse, which we denoted as A prime. Now, I just multiply A prime in the equation BA into A prime equal to CA into A prime. Since we are in the group, associate law holds, therefore, I can able to interchange the brackets. So, B into A cross A prime, which is equal to C into A cross A prime. Now, what happens? A and A prime are inverses, because A prime is A inverse, therefore, this is an identity, therefore, B into E. Similarly, here also this is identity, therefore, C into A. We know by identity axiom B into A is B, C into E equal to C, therefore, B equal to C. So, we have proved the left cancellation, therefore, we proved the right cancellation law. Similarly, the left cancellation law also valid, therefore, cancellation law is valid in case of group. Finally, we move on to uniqueness of inverse, which means that in a group every element has a unique inverse. So, let G be a group and A is an element of G. So, just assume that suppose A has two different inverse, namely B and C. So, I take B and C are the inverse of A inverse. Okay. Now, what happened? We have chosen that there are two inverse for A, B and C. Therefore, A into B is E, because B is the inverse of A. Again, C is inverse of A, therefore, A into C again E. Therefore, AB equal to E and AC equal to E. Therefore, these two E are equal, therefore, left hand sides are equal, therefore, AB equal to AC. Now, we have just seen that cancellation law is valid in case of group. So, I apply the cancellation law, I just cancel A and A, which I get B equal to C. Therefore, if B and C are the two different inverse of A, then the two difference is nothing but both of them are same. Hence, every element has unique inverse. Conclusion. Dear learners, now we are at the end of the session. Let us recall the basic concepts of groups once again. First, we discuss about the binary operations, which plays key role to form a group. Then, by using the binary operation, we define a group which is nothing but a non-empty set that satisfies closure property, associative property, identity property and inverse property under the given operation. Also, we define monoid and semigroups. Moreover, we add one more property to the group, which is commutative property. Using the commutative property, we classified the groups into abelian or non-abelian. After we had verified several sets with its operation form a group or not, we had classified the sets into its group property in the tabular format. In addition to that, we had seen some results like uniqueness of identity and inverse. There are more basic concepts of group theory Further concepts of group theory will discuss in the upcoming session. I hope this session gave you a basic idea of group theory. So, we will meet in the upcoming sections. Stay with us. Thank you.